Domain of a symbolic function. So recall first of all, the domain is the set of all inputs. When we were finding the domain from a graph, that meant the set of all x values, and we could visualize what those x values are from looking at the graph. When we're dealing with a function that's defined like a formula, like this g of x equals 1 over x plus 2, finding the domain is a very different kind of process. What we're going to interpret that domain as now is the set of all allowable inputs. That means, imagine that we start with the whole set of real numbers and we only take out the ones that are going to give us some sort of error in our computation. So division by 0 is the primary source of computation error that we're going to be looking for at this stage. Later in the course, we'll also get into square roots and see that they have a restricted domain. If you go on to college algebra, you'll also get into log functions, which have a restricted domain. So as our repertoire of functions increases, the number of special cases that we have to look for in domain also increases. Right now, all we're looking for is division by 0 errors. And that means if I'm looking at, for example, this first function, g of x, equals 1 over x plus 2, I could start by just trying to see what value of x might give me a division by 0 error here. If I don't just see, maybe negative 2 might occur to us, because plugging in negative 2 for x here would give us one over negative 2 plus 2, which would be 1 over 0, which would be undefined. So one way to see what those values are is just by imagining what might make that denominator equal to 0. However, it's not always possible to just look at the expression and see what that value is going to be, so we also want to have a process. We're going to exclude from the domain all x that make the denominator 0, and the way we can find those values is just by taking the denominator out and setting up a little equation, but instead of an equals, I'm going to use a not equals. So what we're saying our restriction is that the denominator, x plus 2, cannot equal 0. When I subtract 2 from both sides, I then get the statement that x cannot equal negative 2. So I can find this result from actually solving an equation if I don't see it from just observing and imagining what that value might be. So this domain is going to be in set builder notation, the set of all x such that x is not equal to negative 2. Going on to the next example, h of x equals the absolute value of x minus 5, we see that there is no denominator. If there's no denominator, or even if there's just no variable in the denominator, then there's no danger of division by 0, and therefore our domain is the set of all real numbers, which we could alternatively write in interval notation as the interval from negative infinity to infinity. The shortest way of saying the set of all real numbers is using the bold R that denotes this set. Now going on to the next two, m of x equals 5x squared minus 7, and n of x equals x minus 5 over 2x minus 6. Take a moment to think about which of those would have a restricted domain. And if you chose n of x, then I agree, because n of x has a denominator. Again, all I do is I take this denominator out and set it not equal to 0. I don't care what the numerator is. The numerator does not matter. Just like the expression in the absolute value in the last one we did didn't matter. The numerator doesn't matter at all. All we care about is a denominator equaling 0, so we're just going to solve this as though it were a regular equation. 2x can't equal 6, which means that x cannot equal positive 3. And I'll go ahead and put that in set builder notation. The set of all x such that x is not equal to 3. Coming back up to my m of x, we decided this one does not have any restrictions for the same reason as the one above it. It has no denominator again, and therefore it has no danger of division by 0, and its domain is all real numbers, or again, the interval from -infinity to infinity.